Welcome back. In the first two lessons, we built models from weighted features and learned how observations become equations in the unknown parameters. We also discovered the obstacle that motivates this lesson. Real observations often conflict with exact equality. Now I'm going to guide you from exact matrix inversion to the best approximate relationship. We will derive least squares algebraically, then rebuild the same answer geometrically as an orthogonal projection. Special care is needed here. The projection happens in observation space onto the column space of the design matrix. By the end, the formula, the residual, the right angle, and the fitted line will all describe one coherent solution. Let us begin with the shared structure. A line uses an intercept and slope. A multiple input model adds one weighted contribution for each input. A basis function model replaces raw inputs by selected transformations, but the unknown weights still enter through a sum. The symbol y hat is a prediction, while y is an observed output. Across all these models, the central reverse problem is the same. Observations and chosen features are known, while the shared parameter vector must be determined. Lesson 2 organized all observation equations as y equals capital Phi times w. Now, the vector y contains the observed outputs. The design matrix Phi contains one evaluated feature row per observation. The vector w contains the unknown parameters. If the observations come exactly from the selected model, equality is possible. But if measurement noise, missing variables, or model mismatch are present, y may not equal Phi times w for any parameter vector. That is the boundary between exact solving and approximation. Return to two exact observations, 1, 3, and 2, 5. Now under the line model, the first gives 3 equals w0 plus w1. The second gives 5 equals w0 plus 2w1. And now subtracting eliminates the intercept, so w1 equals 2. Substituting back gives w0 equals 1. The fitted relationship is y hat equals 1 plus 2x. This familiar simultaneous equation solution will give us a trustworthy reference while we introduce matrix inversion. Write the same equations in matrix form. The observed vector is 3, 5. The design matrix has rows 1, 1 and 1, 2. The first column of 1s belongs to the intercept. The second column contains the input values. Multiplying this matrix by w0, w1 reproduces the two scalar equations exactly. Matrix notation is not replacing the reasoning, it is arranging the reasoning, so the same operations extend to larger systems. For an ordinary, non-zero number, multiplication by its reciprocal undoes multiplication by the number. A matrix inverse plays the corresponding role for a reversible linear transformation. If phi is invertible, phi inverse times phi equals the identity matrix. The identity leaves every vector unchanged. This is an operation statement, not ordinary division. Matrix multiplication has an order, so we must multiply from the correct side. Starting from y equals phi w, multiply both sides on the left by phi inverse. The right side becomes phi inverse phi w. Because phi inverse phi is the identity, the right side reduces to w. Therefore, w equals phi inverse y. Notice the order. Phi inverse multiplies y from the left. This formula solves an exact system only when the ordinary inverse exists. For a 2 by 2 matrix with entries A, B, C, and D, the inverse uses the determinant AD minus BC. Now, I'm going to guide you through this idea. Swap the diagonal entries, negate the off-diagonal entries, and divide by the determinant. Notice what happens here. This construction is valid only when the determinant is non-zero. A zero determinant means the transformation has collapsed at least one direction, so it cannot be uniquely undone. For our design matrix, the determinant is 1 times 2 minus 1 times 1, which equals 1. The inverse is therefore the matrix with rows 2, -1, and -1, 1. Multiplying by the observed vector 3, 5 gives W0 equal to 2 times 3 minus 5, which is 1. It gives W1 equal to negative 3 plus 5, which is 2. Matrix inversion and ordinary elimination agree, as they must. The ordinary inverse formula requires two conditions. Phi must be square, so the number of observations equals the number of parameters. It must also have full rank, so those equations contain independent information. Square shape alone is not sufficient. A square rank-deficient matrix has no inverse. Under both conditions, an exact system has one unique parameter vector. Now collect 5 points on the exact line 1 plus 2x. Phi has 5 rows and 2 columns, so it is rectangular and has no ordinary inverse. Yet the parameter vector 1, 2 satisfies every row. This is crucial. Lack of a square matrix inverse does not mean that no solution exists. It means only that phi inverse is not the correct operation. A tall system is exactly solvable whenever the observed vector lies among the predictions the columns can generate. With exact measurements, the minimum number of independent observations may be enough. With noise, trusting only the minimum is risky. Imagine 5 points near 1 plus 2x. A line through the first two differs from a line through the first and third, and differs again from a line through the last two. Each pair contains its own accidental errors. More informative observations let us combine evidence about the shared relationship rather than letting one noisy pair dominate. The careful statement is that more independent, informative, representative observations usually reduce random estimation uncertainty. This depends on useful variation and on errors that do not always push in the same direction. More rows do not automatically remove systematic bias, duplicated information, rank deficiency, missing inputs, or an inappropriate model family. More data help us estimate the chosen relationship more precisely. They do not guarantee that the chosen relationship is scientifically correct. Before fitting a line, consider a constant model with one unknown value, mu. 5 measurements are 9.7, 10.4, 9.9, 10.2, and 9.8. Any single reading may be high or low. Their average is exactly 10 in this example. Positive and negative deviations partly balance. This does not prove that every average is correct, but it makes the core intuition tangible. Combining independent measurements can be more stable than trusting one measurement. Now, I'm going to guide you through this idea. For observation I, write y sub I equals y hat sub I plus epsilon sub I. Epsilon represents the part of the observation not explained by the model prediction. In a general basis function model, the weighted feature sum plus epsilon produces the observation. Stacking all rows gives y equals phi w plus epsilon. Because epsilon is generally non-zero, the strict equation y equals phi w may be impossible for the observed data. We instead seek phi w approximately equal to y. Not every disagreement is random measurement noise. Individual observations may fluctuate around an appropriate model, but the chosen family may also be too limited. If the true pattern is y equals x squared, and we insist on a line, even perfect measurements cannot all be reproduced. In practice, observation minus prediction may contain both unexplained variation and systematic model mismatch. More data can reveal that structure, but cannot turn an unsuitable family into the true relationship. Consider the points 0, 1, 1, 2, and 2, 2. Now, the first equation forces W0 to 1. The second then forces W1 to 1, but those values predict 3 at x equals 2, while the third observation is 2. No single line passes through all 3 points. The matrix equation y equals phi times w has no exact solution. We must now define what we mean by the best approximation. Every candidate parameter vector creates a prediction vector, phi w. Subtract that prediction from the observed vector. The result, r equals y minus phi w, is the residual vector. A positive entry means the observation lies above the prediction. A negative entry means it lies below. A zero entry is an exact match. In an inconsistent system, the residual cannot be zero for every component. Our question becomes, how should we choose w so that this residual vector is as small as possible? Least squares measures residual size by squaring every component and adding. The sum of squared errors is r1 squared through rn squared. In vector notation, this is the squared Euclidean length of y minus phi w. The entire dataset is now summarized by one non-negative scalar objective. A perfect fit gives 0. Otherwise, smaller values mean the prediction vector is closer to the observation vector under Euclidean distance. If residuals are +2 and -2, their ordinary sum is 0, even though neither observation is fitted. Squaring counts both disagreements. Squaring also gives larger errors more influence. A residual twice as large contributes 4 times as much. Finally, the squared objective changes smoothly with the parameters, which makes differentiation convenient. A later lesson can add a probabilistic interpretation. Here, squared error gives a precise operational meaning to best fitting. Define j of w as 1/2 the squared residual length. The factor 1/2 does not change where the minimum occurs. It simply cancels a factor of 2 in the derivative. Argmin means the parameter vector at which j reaches its minimum. You can picture j as a surface above parameter space. For a well-identified linear model, it forms a convex bowl, and the least squares estimate sits at the bottom. The squared Euclidean norm can be written as a dot product. Transpose the residual column vector, multiply it by the residual, and add the component-wise products. This gives exactly the sum of squared residuals. Writing the objective this way exposes the matrix structure we need for differentiation. Expand the product carefully. The first term, y transpose y, does not depend on w. The two cross terms combine into -2w transpose phi transpose y. The final term is w transpose phi y. The objective is therefore a quadratic function of the parameters. This algebraic bowl is the same surface we just pictured. Differentiate j with respect to the parameter vector. The gradient is phi transpose phi w minus phi transpose y. Equivalently, it is phi transpose times prediction minus observation. The gradient contains one partial derivative per parameter and points in the direction of steepest increase. At the bottom of the differentiable convex bowl, there is no downhill direction left, so the gradient is 0. At the minimum, substitute w hat and set the gradient to 0. Now, phi transpose times phi w hat minus y equals 0. Rearranging gives phi transpose phi w hat equals phi transpose y. These are the normal equations. The word normal will gain geometric meaning shortly. It refers to a perpendicular, or normal, residual. Track the dimensions. Phi is n by p. Phi transpose is p by n. Their product, phi transpose phi, is p by p, while phi transpose y is p by 1. So the normal equations form a square system in the key unknown weights, even when the original design matrix is tall. But this multiplication is not merely a device for manufacturing a square matrix. The geometry will explain why phi transpose is exactly the correct operation. If phi has full column rank, phi transpose phi is invertible. Multiplying the normal equations by its inverse gives w hat equals the inverse of phi transpose phi times phi transpose y. Keep the entire expression together. The inverse alone is not the solution, and phi transpose y must not be omitted. This is a closed form ordinary least squares estimate. Algebraically, least squares replaced an approximate rectangular system by square normal equations. It would be easy to remember this as a trick. Multiply both sides by phi transpose. That memory is incomplete. Phi transpose appears because it measures dot products with every column of phi. Those dot products express the condition that the residual has no component left in any prediction direction. Let the columns of phi be phi 0 through phi p minus 1. Multiplying by w forms a weighted combination of those columns. Therefore, every prediction vector belongs to their span, called the column space of phi. This is the complete set of output vectors the selected model can produce at the observed inputs. Changing w moves within this model space. It cannot move outside it. For inputs 0, 1, and 2, the line design matrix has columns 1, 1, 1, and 0, 1, 2. Now, because there are 3 observations, a complete output vector is a point in 3-dimensional observation space. The 2 independent design columns span a plane through the origin. Every possible line prediction across these 3 inputs is one point on that plane. This plane, not the line in the ordinary XY plot, is the geometric model space for the 3 output vector. If the 3 observations lie exactly on some straight line model, their vector y lies in the column space plane. A parameter vector reaches that point exactly, so y equals phi w, and a residual is 0. In this case, projection does nothing because y is already in the model space. With noisy or mismatched observations, y usually lies outside the column space. No movement of the weights can reach it because weight changes remain within the plane. The problem is no longer to solve phi w equals y. It is to find the reachable point on the plane that is closest to y. All the closest reachable prediction y hat. Now, because it is a model prediction, y hat equals phi w hat. Geometrically, y hat is the orthogonal projection of y onto the column space. The residual, y minus y hat, is the connecting vector from the projected point to the observation. The word orthogonal means that this connecting vector meets the model space at a right angle. Suppose the residual still had a component lying along the model plane. Then we could slide the prediction a little in that in-plane direction and reduce the distance to y. The original point would not have been closest. At the true closest point, no in-plane residual component remains. The residual points entirely outside the space and is perpendicular to every direction within it. This is the same reason the shortest path from a point to a line or plane is perpendicular. The columns of phi span the model space. A residual is perpendicular to the whole space exactly when its dot product with every spanning column is 0. Phi transpose r collects all those column residual dot products into one vector. Therefore, perpendicularity becomes phi transpose r equals 0. This is why the transpose appears. It is performing every required orthogonality test at once. Substitute r equals y minus phi w hat into the orthogonality condition. Now, phi transpose times y minus phi w hat equals 0. Expanding and rearranging gives phi transpose phi w hat equals phi transpose y. Let us pause on that. These are exactly the normal equations produced by differentiation. Optimization says the gradient vanishes. Geometry says the residual is perpendicular. They are the same mathematical statement. We have reached the same equation along 2 routes. Least squares chooses the weights that minimize squared Euclidean distance. Projection chooses the closest point in the column space and requires a perpendicular residual. Both routes lead to the same w hat and the same fitted vector. They are not competing methods. They are 2 views of one result. State the target space precisely. The observation vector y is projected onto the column space of phi, not the column space of phi transpose. Prediction vectors have the form phi w, so they live in col phi. Phi transpose appears only because it gathers inner products between a residual and the columns of phi. Confusing these 2 roles leads to an incorrect geometric picture. Substitute the closed form weights into, and let's write this down, y hat equals phi times w hat. The result is phi times the inverse of phi transpose phi times phi transpose y. Now define the matrix multiplying y as p, then y hat equals py. The residual is y minus py, or I minus p times y. P keeps the component inside the model space, I minus p keeps the perpendicular component. An orthogonal projection matrix is symmetric. P transpose equals P. It is also idempotent. P squared equals P. Projecting twice gives the same result as projecting once. If a vector already lies in the model space, P leaves it unchanged. These properties encode the geometric idea that projection separates a vector into an in-space component and a perpendicular component without repeatedly moving the in-space part. Return to the inconsistent observations 0, 1, 1, 2, 2, and 2, 2. Now the line design matrix has rows 1, 0, 1, 1, and 1, 2. The observed vector is 1, 2, 2. We will now calculate the least square solution completely, then verify both its residuals and its projection geometry. First, transpose phi. Now multiply phi transpose by phi. Each entry is a dot product between two design columns. The intercept column dotted with itself gives 3. The cross dot product gives 3 in both symmetric positions. The slope column dotted with itself gives 5. Therefore, phi transpose phi has rows 3, 3, and 3, 5. Now, I'm going to guide you through this idea, and we'll do it step by step. Next, compute phi transpose I. The first component sums the observed outputs, giving 5. The second weights them by input 0, 1, and 2, giving 6. These values measure how the observation vector aligns with each design column. The normal equations are now the matrix 3, 3, 3, 5 times w hat equal to 5, 6. Notice how the structure of these equations reflects the alignment we just computed. The determinant of the normal matrix is 15 minus 9, which is 6. Its inverse is 1/6 times the matrix 5, negative 3, negative 3, 3. In simplified form, the rows are 5/6, negative 1/2, and negative 1/2, 1/2. The non-zero determinant confirms full column rank in this example. Multiply the inverse by 5/6. The intercept is 25/6 minus 3, which is 7/6. The slope is negative 5/2 plus 3, which is 1/2. Therefore, the fitted line is y hat equals 7/6 plus 1/2 x, or approximately 1.167 plus 0.5x. It does not pass through every point. It is optimal under the squared residual criterion. Evaluate the line at 0, 1, and 2. The predictions are 7/6, 5/3, and 13/6. Approximately, these are 1.167, 1.667, and 2.167. Stacked together, this fitted vector lies exactly in the column space because it was constructed as phi w hat. Subtract prediction from observation. The residual vector is negative 1/6, 1/3, negative 1/6. The first and third observations lie below their predictions, while the middle observation lies above. The residual is not 0 because exact fitting is impossible. Least squares makes its squared Euclidean length as small as any line can achieve. Now perform the decisive check. Dot the residual with the intercept column. Negative 1/6 plus 1/3 minus 1/6 equals 0. Dot it with the slope column. 0 plus 1/3 minus 2/6 also equals 0. Phi transpose r is the 0 vector. The residual is perpendicular to both spanning columns, confirming that the fitted vector is the orthogonal projection of y onto pol phi. There are two geometric pictures, and we must not merge them carelessly. In the ordinary xy graph, each observation is a point, and the fitted line is drawn across the plane. Ordinary least squares holds each x value fixed and measures the vertical output difference, y sub I minus y hat sub I. These vertical segments are the scalar residuals shown in the familiar data plot. In observation space, the whole collection of n observed outputs is one vector y. Every complete prediction vector lies in call phi. The fitted vector is the projection onto that subspace, and the complete residual vector is perpendicular to it. When n is 3, we can draw this directly. See, a larger n, the same geometry remains valid, even though we cannot visualize every dimension. Ordinary least squares does not generally minimize perpendicular distances from plotted points to the line in the xy graph. It minimizes squared vertical output residuals. Stack those vertical residual values into one vector, and that vector is perpendicular to the design column space in observation space. The right angle belongs to the vector space picture, not necessarily to each point-to-line segment in the original graph. Suppose the model is appropriate, and measurement errors are independent, centered around 0, and have finite variation. As informative observations accumulate, positive and negative errors tend to balance, individual unusual measurements have less influence, and parameter estimates become more stable. In many common settings, estimation uncertainty decreases roughly like 1 over the square root of n. This is a rate of improved precision, not a promise that all error disappears. More data are not magical. If every instrument reads 5 units too high, averaging preserves the bias. Copying one observation 1,000 times does not create independent information. If feature columns always move together, additional rows with the same dependency do not identify separate effects. If the true relationship is curved, more data may determine the best line more precisely, but the line remains an approximation. Representative information and modeling assumptions matter as much as row count. Compare 3 cases. In a square, full-rank exact system, ordinary inversion gives W. In a tall exact system, no ordinary phi inverse exists, but y still lies in col phi, and the least squares residual is 0. In a tall noisy system, y lies outside the column space, and least squares returns the closest reachable prediction. The normal equations cover both tall cases. The residual tells us whether the fit happened to be exact. For a tall, full column length matrix, the expression inverse phi transpose phi times phi transpose is a form of the Moore-Penrose pseudo-inverse. Write it as phi plus. Then W hat is phi plus y. If phi is square and invertible, the pseudo-inverse reduces to the ordinary inverse. The full pseudo-inverse also handles rank-deficient cases, but that broader theory can wait. Here it provides one compact language for exact and approximate linear systems. The closed-form formula is mathematically important, but it is not usually the best numerical recipe. Forming phi transpose phi can worsen conditioning, and explicitly calculating an inverse can add unnecessary numerical error. Practical software typically uses QR decomposition, singular value decomposition, or a specialized least squares solver. Learn the formula for its structure and interpretation. Use stable solvers for serious computation. The inverse formula requires full column rank. Now, let us build this step by step. If phi has rank below p, then the matrix phi transpose phi is singular and its inverse does not exist. Notice what happens here. An optimal fitted prediction may still exist, but several parameter vectors can produce it. A non-zero movement in a null direction changes the weights without changing predictions. The Moore-Penrose pseudo-inverse can select a standard minimum norm solution. Keep this distinction in mind. The distinction between unique prediction and unique parameters remains essential. Under full column rank, 6 descriptions identify the same answer. What minimizes squared residual length? The gradient is 0. The normal equations hold. The closed-form formula solves them. A fitted vector is the orthogonal projection of y onto col phi, and the residual is perpendicular to that column space. These are not separate answers to memorize. They are translations between optimization, algebra, and geometry. Pause for the first check. Phi has rows 1, 0 and 1, 1. Y is 2, 5. What are the weights? The first row gives W0 equals 2. The second gives W0 plus W1 equals 5, so W1 equals 3. The exact model is y hat equals 2 plus 3x. Suppose a line model has 2 parameters and 10 observations. Let me draw that scene in your mind's eye. Now, does this automatically mean no exact solution exists? No. If all 10 points lie exactly on one line, one parameter pair satisfies every equation. The system is overdetermined, but consistent. Let us keep in mind that noise usually creates conflict. The rectangular shape alone does not. Onto which space is y projected? Onto the column space of phi. Now, why does phi transpose appear? Because phi transpose r collects the residuals dot products with the columns of phi. The target space and the orthogonality test are related, but they are not the same object. Start from r equals y minus phi times w hat, and the condition phi transpose times r equals 0. Now substitute the residual, giving phi transpose times y minus phi times weight hat equals 0. We distribute and then rearrange. The result is phi transpose phi times w hat equals phi transpose y, the normal equations. Let us correct 4 tempting shortcuts. Exactly as many observations as parameters is not enough. Independence is also required. A rectangular matrix is not automatically unsolvable. It may have a 0 residual exact solution. More observations reduce random uncertainty only when they add useful information, and do not remove systematic bias by magic. And the projection target is col phi, not col phi transpose. 2 final warnings protect the geometry and computation. Ordinary least squares minimizes vertical output residuals in the xy plot, not perpendicular point-to-line distances. The complete residual vector is perpendicular to col phi in observation space. And while the inverse formula reveals the structure, reliable software should generally solve least squares with QR, SVD, or a dedicated solver instead of explicitly forming the inverse. Let us collect the full progression. Exact square systems can be solved by ordinary inversion when the design matrix is full rank. Real observations often make exact equality impossible. So we define the residual y minus phi w and choose the weights that minimize its squared Euclidean length. Differentiation gives the normal equations. Under full column rank, the closed form solution is inverse phi transpose phi times phi transpose y. Geometrically, phi w ranges over the column space. Least squares projects y onto that model space, and the residual is perpendicular to every design column. The formula, the minimum, and the right angle are one result. We now know the least squares solution in closed form and understand its geometry. But what if phi transpose phi is enormous, nearly singular, or expensive to solve? What if the objective is not squared error? Can we approach the minimum iteratively instead of solving one matrix equation? These questions lead naturally to gradients and gradient descent. In the next lesson, we will turn the gradient from a condition at the solution into a step-by-step algorithm for reaching it.